I will speak today on how I have seen reverse osmosis systems evolve, where or how the technology began, how the RO membrane and associated components work, and some common troubleshooting points wherever I can fit them in, and also how the ROs have changed as far as what I have seen. Now, the physics behind osmosis was discovered, or at least first noted, by a French clergyman and physicist named Jean-Antoine Nollet way back in 1748. Between the 18th and 20th centuries, membrane technology was pretty much only used in a laboratory type condition, but the 1940s saw reverse osmosis develop for desalination purposes. This was great. This technology was then used to make seawater drinkable. This development would allow for women and men to develop this into what we now know today. 1959 saw the first real effective development to RO membranes to benefit us now, and that was the use of polymer materials to manufacture the membranes. Cellulose triacetate, or CTA as we call it in the industry, powered the way as a membrane material, followed by the more effective thin film composite, or TFC, and we continue to primarily use TFC membranes today due to its construction producing water faster and of a higher quality over the CTA. So what does an RO actually do? Well, it reduces, it purifies. It is going to reduce the dissolved salts, metals, minerals, impurities, or contaminants. The taste and the odor and particulates will all be adjusted and reduced in a very favorable fashion. In fact, RO systems typically reduce somewhere in the neighborhood range of about 85 to 98%. So there's always going to be a little bit left over in a reverse osmosis treated water system. But the end result is still going to be much healthier and better tasting water than before the reverse osmosis system. And, in my opinion, it's the most practical method of water purification. Other methods like water distillation, ion exchange resins work incredibly well, but they are costly and they can be complicated. So let's discuss what osmosis and reverse osmosis means. Osmosis, which could also be termed diffusion, is the movement of water molecules through a semi-permeable membrane. If the water molecule concentration was higher in a salt content on one side of the membrane, the lower concentrated side of salt water molecules, or ions, will naturally pass through the membrane to the higher concentration side until an equilibrium is achieved between the two sides in salt concentration. What will also occur by the end of this phenomena is that the higher concentration side will also have a higher level of water due to this movement of high salt concentration water. The higher level is referred to as the result of osmotic pressure. Reverse osmosis is a really great term, in my opinion, because as what happens here is we are taking a force to the higher concentrated side of the semi-permeable membrane to force this concentrated salt levels and the water through the membrane to the lower concentrated side. This is the opposite from the natural movement that occurred during the osmosis animation we just saw. In the case of the reverse osmosis systems that we use, the semi-permeable membrane will allow for a displacement of unwanted molecules or ions to a drainage point. The pore size of the membrane determines how small of a particle or water ion is allowed to pass through to what we would use as our treated water. This is why reverse osmosis, as I said earlier, will always have a small amount of dissolved ions in the produced water that is correctly called, by the way, permeate. The drain or wasted water is correctly called concentrate. Membranes come in different pore sizes. There are other membranes besides reverse osmosis membranes, but I'm going to focus primarily on RO membranes today. But there are some other membranes that could be of interest to some of you for another day's discussion. Generally, we consider three choices for membranes: the RO, then the nano, and ultra membranes. Looking at this chart, you can see examples of common materials and their micron size. The right-hand side of the chart has the largest particles and largest in micron size, and the left has the smallest in micron size. According to this chart, we can see with our naked eye down to around 30, maybe 25 microns at best. After that, we will require microscopes. Sediment cartridges or mesh-type screen strainers that we use in daily water filtration are typically used down to just below 1 micron in size, and then we move into microfiltration cartridges for high levels of particulate reduction. And these are designed down to below 0.1 micron. These high purity cartridges are usually absolute rated cartridges for precise filtration, by the way. Nominally rated budget price cartridges that we typically see on shelves of stores do not assure that any given micron rating on that cartridge will be achieved. Now back to the membrane. The RO membrane to the far left of this chart indicates an estimated micron reduction lower than 0.0001. Did I say that correctly? 0.0001. This is one reason why we need pressure to operate RO systems. We need to force water through the membrane and also discharge the unwanted water molecules or contaminants. We will touch base today on different ways we achieve this. We are going to see an animated overview of how membranes operate. This animation of the flow in a spiral direction through all membranes is typical, and we will show the separation of concentrate from the feed water to allow for clean, permeate water. You will note the water to be treated entering on the right-hand side and discharging on the left-hand side. Note that the left side has two streams of water, the center of the flow, which is the permeate or the purified water, and the stream around that center flow, which is the concentrate or also referred to as brine, but most of us call this brine the waste or reject water. As water is purified by passing through the membrane and collected in a center tube called the permeate tube, impurities are rejected and do not make it through to the permeate tube. The animation on the right-hand side shows feed water in the center, the permeate tube at the top, and the feed channel spacer at the bottom. The feed channel spacer or spacers is where the wastewater or concentrate will go. What you now see are examples of what is allowed to enter the permeate tube. The membrane type is highlighted in green in the bottom right-hand corner, and the animation is showing degree of separation between the permeate and concentrate. Looking at the reverse osmosis, a large percentage of the feed water suspended solids, organics, or microorganisms are not allowed to pass through to the permeate tube. These instead will find their way to the drainage point. NF, which is the nanofiltration, allows more feed water through to the permeate tube. The UF, or ultrafiltration membrane, allows even more feed water to the permeate tube. And finally, microfiltration, allowing the most feed water through to the permeate tube of all membranes. Some microfiltration can be used as a membrane, but primarily, as I said earlier, it's a cartridge. The construction of a membrane has always been interesting to me. If you ever cut an RO membrane open and look at the materials, you will see layers of the feed channel spacers, membranes, and permeate collection material all wrapped around the perforated permeate tube. Feed water impurities pass through to the drain, and water continues to travel in a spiral direction through all those layers to the permeate tube. Really quite interesting. I want to give a special shout out to our friends at Suez Membranes for creating this animation. It's a good one. One slide I always like to go over is in regards to the terminology we use, or shall I say, RO speak. It is so important that we communicate to each other the basics of RO systems and the technology. RO is the abbreviation for reverse osmosis, in case some of you actually didn't know. TDS, or total dissolved solids, this is the number reflected by the total amount of mineral salts, ions, or whatever else is in the water that naturally occurs through the hydrological path of water. We use TDS as a measurement of the water, or I should say the measurement of the RO water quality, or lack thereof. Flow control, or restrictor, this controls the flow to drain of the concentrate out of the membrane. This must be a predetermined amount based on the membrane size. This is an important part, as this flow restriction is what will force the feed water to travel through the membrane to the permeate tube at the appropriate flow rate and pressure. Recovery rating is the percentage of incoming feed water that ends up as permeate water. The recovery rating does not take into consideration the use of a storage tank or any other components that are part of the RO system, just the membrane. Reject rating is the percentage of incoming feed water not used as permeate water and would be sent to the drain as concentrate. The ratio is the difference or delta percentage between the volume or recoveries of the permeate and the concentrate flows that are coming directly out of the membrane itself. Back pressure is what occurs to the under the sink or residential RO systems which use an air captive bladder style storage tank. Efficiency rating is the percentage of the incoming water available as purified or permeate water under normal operating conditions. The efficiency takes into consideration the use of the air storage tank, back pressure on the membrane, and other factors due to cartridges, fittings, etc. This is considered more accurate than the previously mentioned recovery rate often used with membrane specifications. Efficiency is relating to the actual complete system that is in use, or I should say under normal use, in people's homes. Temperature correction is what we need to consider on any and all RO systems, for that matter, used on water colder than 77 degrees Fahrenheit or 25 degrees Celsius. 25C and 77F is the temperature factories test membranes at as a universal standard. Colder water decreases membrane production of permeate or purified water. We need to adjust our expectations when we use these systems on colder water, such as here in Canada. For an example, a 50 gallon per day membrane will produce 44 gallons per day on 21.1 degrees Celsius water. That same membrane on 10 degrees Celsius water will only produce 29 gallons per day. RO systems have come in many different shapes, sizes, methods of operation. There have been similarities and many differences between RO systems over the years. All these systems attempting to have one more feature over another to create more of a benefit for the consumer, thus the sale. Multiple cartridges have been used, pumps that create faster production or better quality and also avoid excess wastewater. Plus there are countertop models that require little installation and many more that I simply do not have the time to show or talk about. But understanding the basics of an RO system for domestic use will allow you the flexibility to make your own educated decision of which model is the best for your business to sell. Domestic, residential, or under the sink RO systems all have necessary components or parts to operate. You see a 4-stage RO system drawing here on the presentation. And 4-stage, I should say, means that there are 4 points of actual filtration used on this drawing. 2 pre-filters, which treat the water for particulates or chemicals such as chlorine, before the water enters the membrane for purification. The membrane would be considered the 3rd stage in this drawing, and there is a post-filter utilized. This 4th stage filter is after the membrane to help with taste or filtration requirements, and any additional filtration added, such as a 3rd pre-filter, would change this drawing to a 5-stage system, and so on if further filtration points were used. A shut-off valve is used on this system, and it's used to shut off incoming water flow when the storage tank is full. This would, in turn, stop all flow of concentrate or wastewater to the drain. You can see a storage tank, the dedicated faucet for dispensing water, a check valve which prevents the stored water that is under pressure from flowing back through the membrane in the opposite direction intended during the production. If a check valve fails, storage tank water could flow back through the membrane and down the drain, or possibly even restrict membrane flow to the storage tank, which in turn would result in no water in the storage tank. A vital part to the RO system is the concentrate flow restrictor or flow control. This controls the wastewater flow rate to drain to allow for proper membrane operation. The flow control could be an inline control or a capillary style that inserts into the drain line tubing. I suggest that these controls are changed with every membrane changeout to ensure efficient operation of the system. A dirty or plugged flow restrictor will result in a premature breakdown of a membrane. First thing that will be noticed of a membrane failing is usually water quality. Production will decline or cease to produce water in an even more serious situation. Membranes produce water slowly. This means that RO systems require storage tanks and a means to pressurize the stored water for usage. Typically, in-home RO systems, the tank is an air bladder storage tank. This tank has the air captive within the tank, and as water fills the tank, the air compresses and creates a back pressure to drive the stored water out of the tank to the dispensing point of drinking water. This works very well for this purpose. However, the back pressure building inside the storage tank does impact the membrane's permeate production. The production slows down as the tank fills. Additionally, these storage tanks need to be large enough to hold both the stored water and the air cell. Let's look at this one more time. The issue with membrane production slowing down due to the storage tank back pressure is that the wastewater or concentrate flowing down the drain is also not slowing down. The issue with membrane production slowing down due to the storage tank back pressure is the wastewater or the concentrate flowing down the drain. The slowing of the production flow rate does not in turn slow the wastewater flow rate. This means that the ratio of the recovery and the reject will increase, and increase a lot, I may add. I have personally tested systems that have had a ratio of 4 parts of water to waste for every 1 part of water to storage when the storage tank was empty. Or in other words, that would have been the ratio of the membrane. But only to discover ratios of 20-1 and even 30-1 as the tanks filled. Now we're talking about the efficiency of the RO system. It is both remarkable and alarming to realize how much water is actually lost down the drain. However, the good news is RO systems have changed over the years and fortunately have become more efficient as time has rolled by. Speaking of ROs changing over the years brings us to the evolution of RO systems. Gravity dispensing RO systems have been around for a long time and are still in use. Basically, the incoming water is allowed to drip into an atmospheric tank, hence the word open bucket design. The great feature here is the lack of back pressure on the membrane due to the absence of a pressurized storage tank. The lack of back pressure achieves excellent efficiencies and low waste to product ratios. The production is maximized. Drawbacks to this design are that these systems are not airtight, thus are potentially exposed to airborne bacteria. They are bulky and take up counter space. They are not practical for under the sink and not easily expandable to a large system with higher production or more than 1 point of use, such as a fridge water dispenser or ice maker. But for consumers on the move or on vacation in an RV, this could be an excellent option. The traditional under-the-sink RO system is likely familiar to most of all of you viewing. You can see images of 5-stage under-the-sink systems using air captive storage tanks. The air cell in these tanks are pre-charged with 5 to 8 pounds of air, psi of air, and this air amount is important, as too much air will impact the operation of the system and also take up valuable storage space in the tank. Too less, and you will have little to no water pressure in the tank. Another point to consider is that air cells do lose air over time and need to be recharged. One point to remember is that these air captive tanks do gradually start to decline in water pressure and flow as you draw water from the system, or in other words, empty the storage tank. So if you were filling a large pot for your pasta boiling, you would probably notice it. The auto shutoff is designed to shut off the incoming water supply when the tank pressures reach a predetermined percentage of the feed water pressure. You know, typically these shutoffs are shutting off at around 60% of the incoming water pressure from the home. A great feature with multiple cartridges is customization of cartridge arrangement to deal with the raw water quality. This allows you different size sediment cartridges. It can also allow you to utilize specialty carbon cartridges. And you know, you can even now use cartridges that are becoming so much more popular, like alkalinity media cartridges for flavor or pH adjustment. This of course means that you've got excellent diversity with these designs. But that said, because there are so many parts associated with this design, to an inexperienced person, it could look pretty complicated. There has always been a complaint about how much space these systems take up under the sink, and when I was an installer, I used to always look for an alternate installation area, such as the basement or an adjoining room. The design has excellent reject flow rates. There is no doubt that a properly installed and applied traditional RO system will produce excellent quality water. However, with this advantage comes the ever-increasing amount of wastewater as the system fills the storage tank. RO faucets are available in many designs and colors to match the homeowner's decor or budget. However, two functions should be discussed of the RO faucet: the standard non-air gap and the air-gapped faucet. The air-gap faucet is seen on the left. It has 3 tube connections and a pre-drilled hole in the faucet body, seen here at between the 11 and 12 o'clock positions of the circle. This hole is the air gap. The drain tube is generally a 1/4 inch diameter in size on under the sink RO systems. That tube would attach to the appropriate fitting on the air gap faucet. A second length of tubing that is 3/8 in diameter is attached to the appropriate fitting on the air gap faucet and attached to the drain pipe fitting with the included RO installation kit. If the house drain or drain connection was ever compromised or plugged, the RO system drain water would discharge out the faucet air gap hole and spill on the sink or the countertop. But the point of any air gap design is to prevent the drain water from entering the RO system. In fact, in most communities, it is a plumbing code to use an air gap. There are other methods of air gaps, and certainly reach out to your supplier for more information about air gap choices. Using a different style air gap than the air gap faucet would allow you, to use the non-air gap faucet. The long tube seen on both of these faucets attached to the permeate line from the storage tank and post cartridge. Pump options are also an important part to RO systems. They aid in speed of production. They help achieve higher quality permeate water and higher storage tank pressure. The booster pump you see here is typically used to feed incoming water into the RO system when the TDS is high. I personally recommend a booster pump on TDS over 700 parts per million or milligrams per liter. Parts per million and milligrams per liter, for all argument's sake, are the same amount. You see a pressure switch which is located on the storage tank tubing, and it turns the pump on and off as required based on the pressure tank's pressure. You also see a power supply. I want to say a little bit about the pressure required for RO membranes here. Physics tell us that 1 psi is required for every 100 part per million or milligram per liter of TDS to just start the reverse osmosis process. That means if you had 500 TDS in the raw water, it will take 5 psi to just start the process of reverse osmosis. However, what is not taken into consideration with this equation is pressure lost or needed to push household water through all of the cartridges, the fittings, and overcome the storage tank back pressure. Add the pressure loss in a home during regular household use, such as flushing of toilets, laundry, or other water usage points. Plus, if the home had low pressure to begin with, all this would add up to an RO possibly or potentially performing poorly. This is why pumps are very helpful to traditional RO systems with air captive storage tanks. And here is the Permeate Pump. The Permeate Pump is a pump I want to point out, as this pump is a great feature in my opinion to reduce wastewater and also create higher pressure in the storage tank by forcing more water into an air captive storage tank. The more water stored in an air bladder tank, the higher the delivery water pressure through the faucet or at the fridge. The Permeate Pump's operation fills the storage tank faster and thus allows an RO system to shut off sooner. This reduces a significant amount of wastewater. Another good feature of the Permeate Pump is the reduction of back pressure to the membrane by its operation. This will actually help the membrane produce a higher quality of water. On a small storage tank, you will certainly notice the pressure decline from the faucet during a long fill of something like a pot of water boiling that great old spaghetti you were going to have for dinner. They can be noisy, however, due to a piston design. And certainly assembly can be confusing. Hey, but like anything else in life, practice makes perfect. Here is a great animation of the Permeate Pump in action. Many of you who have done business with me have seen this, I'm sure. But allow me to take you through its operation. Starting on the left, you see the pre-filters and 75 psi as an example of incoming water pressure from the home. The water is going to pass through the two pre-filters that you see in this particular animation, and the water is now going to pass through into the membrane through the hydraulic shutoff. Now let's just ignore the pump as well as the magnifying glass just for a moment. So the water coming out of that membrane or RO module will leave the RO module, the permeate that is, will leave the RO module and enter into the storage tank. You can see the black line coming out of the RO module is the concentrate, and it's going through its flow restrictor and traveling to the drainage point. As that storage tank fills up, the hydraulic shutoff, you can see, has a line coming from the storage tank area, and as that storage tank fills up to a point that moves the hydraulic shutoff diaphragm to a shutoff position, that hydraulic shutoff will shut off the incoming water. Now, going back to the Permeate Pump and magnifying glass now for a minute, you can see in this animation the estimated PSI of the RO or permeate water coming out of the RO membrane is 5 PSI. And the reason is water always takes the least point of resistance. So in the case of a membrane, the concentrate or wastewater or the incoming water coming through that membrane is really going to try and go through to the drainage line. That's why we need a flow restrictor, because that flow restrictor is going to put the brakes on that water and force it to back up in a spiral direction through that membrane to the permeate tube. But the pressure coming out of that permeate tube is extremely low. So this pump, and one of the things that is great about this pump is it requires no electricity. It functions from the hydraulic flow of the drain water or concentrate water coming out of the membrane through the flow restrictor. So you can see that black line. It's feeding the permeate pump and driving the piston, which is driving the diaphragm on the right hand side of that pump. It's allowing the permeate water to flow into the pump, and that pump is pushing that water into that storage tank. I assure you, that storage tank is going to fill up with a significant amount of water than that RO system will ever put in that storage tank without this permeate pump. You can see in this diagram here, the tank is starting with an 8 psi pre-charge. In other words, it's empty of water. And then as it fills up from this permeate pump, it's driving it to approximately 60 psi with a 75 psi incoming water pressure. The end result is that this permeate pump is going to fill this storage tank faster, and I mean a lot faster than if the RO wasn't being used with a permeate pump, which means the system's going to shut down faster. Another fantastic product is the water-on-water systems. For most of us, a relatively new type of RO system. You can see 3 different types that I've come across, and the one on the bottom right hand corner is the one that the company I work for sells and promotes, and it's pretty darn good. Water on water systems are unique, and it's because they require no air in the storage tank. Think about that, no air. Huh? Yeah, no air. The bladder utilizes water and the household water pressure to squeeze out the water of the storage to the point of use. The product that I'm most familiar with uses only one moving part. This moving part is there to allow water household pressure to squeeze out the permeate water, and then immediately after the use produce more permeate water. The key here is no back pressure to the membrane, and that's because there is no air captive storage tank. Because of this, you will have greater efficiency, which can also afford you higher quality water. There's an even dispensing flow rate because there is no decline of water pressure like a traditional RO storage tank. The only impact on this delivery system will be from the household water pressure. Generally a much smaller footprint than traditional systems, and of course this is a massive selling feature to the consumer, especially if you were to put one of these water on water systems on a table next to a traditional 5-stage RO system. They're going to see the difference. I have seen a few different water on water systems, and there are some that have complex designs and many fittings to create this process. I saw one system that I counted around 90 potential leak points because of the amount of fittings on that system. Because these water on water systems rely 100% on incoming water pressure, they do have some drawbacks, and that is when they are used in high reaching points of use or homes with really low pressure. One thing to note is that a water on water system will not operate if there is a water leak or during water usage. Let's take a look at how these work. This is the operation during dispensing of water. The water is entering from the left-hand side, going into the pre-filter. And you can see the water discharging out of that pre-filter and going into the membrane. But note, there is no water working its way from that membrane into the middle permeate tube. So there is no permeate actually coming out of this membrane right now in this dispensing animation. All the water is actually flushing down the exterior of this membrane and coming out in this diagram in the pink tubing line. That pink tubing line is entering into the single moving part of this unit called the CPU valve. That CPU valve now is driving that water in that pink line or pink tubing down into the storage tank. And look at it squeeze out the purified water in blue out through the post filter and out through the faucet. To the left of that post filter, you can see the pink drainage point. There is no water going to drain at the moment. And that's why we like to say on this particular system that the purified water that's being dispensed out the faucet is being squeezed out of the storage tank. So theoretically speaking, the amount of pressure you have on the inlet going through the pre-filter, I should say, is the same pressure that you should have or see out of that faucet. Now, let's take a look at the production side of this system. Again, water is entering from the left, going through the pre-filter, coming out of the pre-filter, entering into the membrane, but now we see the permeate water coming out of the permeate tube. And it is now pushing its way down into the storage tank. The drainage water, again, is in pink, and it's coming out of the membrane, finding its way into the CPU valve. But what the CPU valve is also doing is allowing the water that we saw in the previous slide that was squeezing out water through the faucet, that water, that is raw water, and then you can see it in pink, red, whatever color you see there, it's coming out of the CPU valve and going out to the drain. Remember, the drain's an open outlet. There is no back pressure on this membrane. None. So what happens now is the membrane is allowed to produce water freely. The storage tank is filling up, but any back pressure that could possibly be in that tank is being discharged out to drain. The other thing is this company promotes the fact that this is a true 2-to-1 RO system, and that's what it's rated at from an efficiency standpoint. There's only one, I'm going to rephrase this, there's only two factors that will affect this RO system as you look at it. One will be temperature of the water. Okay, so the temperature correction rule still applies because, again, we're talking about the effect of cold water on a membrane. And the other factor is incoming pressure. If you only have 30 psi coming into this RO system, then that's all you're going to achieve at best coming out of the faucet. So where do we use an RO? In the home, we use it for drinking water. It's great for ice making. RO water is fantastic for cooking and boiling, rinsing glassware, plants. In industries, we have seen RO being used in car washes. In case you didn't know, you ever go through a car wash and see a spot-free rinse? Now you know. That's RO water. Bakeries, they use RO water for the steam equipment. It's very popular. Stores use it to rinse and mist over produce. And plant growing, especially now with the cannabis industry, because it allows them to start with a high quality water that's not going to be impacted by natural impurities, and in the case of cannabis growers, to the pot. Fish aquariums, electronic manufacturing rinsing. There's a massive industry there of companies and corporations that manufacture electronics. They need high purity water. Medical and dental facilities. I have asked my dentist, what kind of water are you using in there, as he's digging away with his high pressure cold rinsing machine. Like, why do they use ice cold water? I never understood that. But anyways, I guess I should have asked him that, but he did have an RO. It's very popular. So why use an RO? Water from a private source can sometimes be an unknown quality. So it's great to have an RO to use as your security blanket, if you will, for the water that you're drinking. The private source could have high levels of contaminants. It can also have high levels of sodium. These are all common things we see in private water well reports daily. Arsenic. Now, arsenic's a complicated contaminant to remove. An RO is a good option. It's not the only option and not necessarily the best option. Heavy metals such as lead or uranium, and viruses or cysts from shallow water supplies. Water from a municipal source, chemicals, chlorine, and chloramines, which is of course derived from chlorine and ammonia. Volatile organic compounds, VOCs, that's solvents, gasoline, taste and odor. Obviously an RO is fantastic for both of those issues. Inadequate or outdated facilities that force boiled water advisories, and I'm talking about municipalities, has become commonplace. In fact, in the community that I live in, it happens about, I'm going to guess, 17, 20 times a year. Yeah, I'm not exaggerating. It's true. Big signs go up at all the stop signs and all the corners. Boiled water advisory. Of course, we don't worry about it in my home. Enhancing water quality for personal flavor or health concerns. There are a significant available amount of cartridges for a wide range of water problems out there. And in a traditional RO type of environment, you can utilize these cartridges where you need to give the consumer the quality of water they want and also the flavor of water that they're looking for. One of the things that we hear a lot about today is pH adjustment. Bacteria concerns. An RO gives you added particulate protection when your incoming water supply might be high in turbidity. It's one of the issues municipal water supplies have. Along with an RO, an ultraviolet light disinfection is an excellent add-on. It's what I use in my home. The where and why to use an RO that leads to sales. Because now that we know why and how RO systems, how is this going to help our sales? Well, if you look at yourself or your business, and if you're not primarily selling a lot of RO systems, but you're selling backwashing filters and water softeners, an RO system can certainly lead to completing the benefit to the consumer. An RO system, especially when needed, is an obvious, great way to make the water taste better, look cleaner, and certainly is healthier to drink. I have no doubt about it. One of the things I think I mentioned earlier cleaner, and better tasting ice cubes. The glistening clean glassware I mentioned to you earlier. So what we need to do is we need to promote, we need to educate, and include RO systems when needed to the people that are our customers and the consumers. Make sure that they are aware of the options that they have here. It's a great residual product in terms of sales because there are cartridges that need to be replaced. So from a business standpoint, it's a good one. It diversifies into other opportunities. There's the plant growers I mentioned, and of course anything to do with rinse water is also a great opportunity for RO sales. You know, long ago, my first water filtration employer said to me, "Jim, never forget, we help the people whom are our customers. We help them have better lives with the products and services we supply them." You know, I have never forgot this, and I know better now how true this is. We water professionals are a benefit to the consumer. When you are communicating with them, provide them with these benefits and educate them. The RO water is a great way to go. So at this point, I want to thank you all for listening. As you can see, my name is Jim. My friends call me Jimmy. You're all my friends. Call me Jimmy. Director of Sales with Good Water Warehouse. At this point, I'm going to pass this back on to Shelly Peters, and if there's any questions, let's get at it.